Welcome to the class of intelligent product design. We are in the world of sensors, right? Like we started with different types of positional sensors, distance and directional sensors. Then we have talked about different types of optical sensors, which can be based on LED, LDR. Then we have also talked about the issues of the intensity reduction and use of photomultipliers. We have also talked about one of the most important group of such optical sensors called the encoders. And finally, we have talked about the optical fibers. Now, in the optical fibers, there is one interesting application that I will first start, and that is called a fiber Bragg grating sensors. You know about the Bragg grating. The grating is something that you can do on the optical fiber. You can create some kind of etching in it, so that this etching can actually create a diffraction. Now, the etching, the distance between these grating is directly related to the diffraction it is going to generate. Now, suppose I am having a system like this, which is subjected to something like a bending. So, that means you choose a system where you have this marking already given to you, okay? And then you know that corresponding to a light of a particular wavelength, what will be the diffraction pattern. But now, if I expand this system by the application of force, okay, then this grating separation distance also expands, because this whole thing is flexible. So, this distance changes. As this distance changes, that will also correspondingly change the diffraction pattern. So, diffraction pattern will then become a function in a way of the force that the system is subjected to. And this you can have not only for one grating, but you can have a single grating fiber, you can have a multiple grating fibers. So, you can have many gratings patterned in it, okay? Grating n minus 1, grating n to grating 1, and each one is triggered for a particular wavelength. So, thus you can use the fiber Bragg grating sensor very precisely to measure things like the strain, or things like the force indirectly that is applied into a system. So, it is a very important application of optical fiber along with this fiber Bragg grating technology. Another optical technique I also want to tell you before ending these optical type of sensors, this is known as laser Doppler vibrometry. So, what it does is that it sends a laser beam, like let us say a particular laser beam is coming on an object, and the object here is actually getting vibrated, okay, with the help of some shaker. So, suppose if there is an object over which the laser is getting dropped, and the object is sometimes here and sometimes here, because it is vibrating with certain excitation level, with certain amplitude. So, what do we expect? We expect when the object is moving towards this direction, okay, approaching towards the signal, there will be a Doppler effect, there will be a frequency shift, the frequency will be increasing, and when the object is going the reverse direction, then it is the Doppler effect will create so called red shift. That means the frequency, the apparent frequency will decrease. So, thus by observing, so you have a sensor here which is actually measuring this emitted light. So, observing the change in the frequency shift in the emitted, the reflected laser through the, because of the Doppler effect, you can actually measure that what is the velocity of this particular object, okay. So, like that, if you have multiple such systems, you can measure the velocity not only at one point, but at multiple points of a system. This technique is known as laser Doppler vibrometry. It is a very accurate technique. Anyway, so these are the systems that are generally used in a case where the system is not mobile. But let us say we are talking about a mobile system, okay, let's say an automobile, let's say an aircraft. Now, for such a system, you cannot carry a laser Doppler vibrometer. You have to think of a system which is portable. Portability is of major concern in such systems. So, we are coming to a new domain now, and these are much more powerful type of sensors, and we will call them smart sensors. These materials are a part of group of materials which are known as functional materials. And what these functional materials do is that they interchange the energy. For example, they interchange between thermal energy to mechanical energy, electric energy or magnetic energy or sound energy to mechanical energy, generally all other energies to mechanical, and from mechanical to either electric energy or magnetic energy. And they are very much analogous to biological materials, like they are adaptive, they have a cellular function, they are self-sensing, the same system can sense as well as actuate. The actuation part we will talk about later on. So, these are some of the good parts, and also you can embed such a system on another system. So, let us say I have an aircraft wing. Okay. So, the advantage is here that I can have lot of these smart sensors embedded inside the aircraft wing, and since each one of these sensors, let us say, can convert mechanical energy to electrical energy, one of the systems. So, that means at different points you can measure that what is the change in the mechanical system, like what is the stress that is developing, the change of the stress dynamically you can measure, convert it into electrical voltage. And the reason why we said that it is cellular in function, that if you use a standard accelerometer, etc., if something breaks, the whole thing kind of loses the continuity. In this case, it is not like that. Even if a part of the thing chips away here and there, still the entire material works. So, it is like a biological system, it is quite robust. So, the traditional sensors that we have talked of, they are designed for certain performance requirements, so load, speed, lifespan, etc. They cannot modify these specifications. Okay. Whereas, smart systems can accommodate the unpredictable environments, okay, can meet exacting performance requirement. Remember, when I talked that the shift from physical intelligence to embedded intelligence is required to give the adaptivity, then the maximum adaptivity you can get is with the help of a smart system rather than a traditional sensory system. Now, there are a few materials which can be used as smart sensor. One of them is piezoelectric films, it is polyvinyl fluoride. Another is piezoceramic, that is lead zirconate titanate. Then SMA, shape memory alloys, magnetostrictive material terphenol D, and shape memory alloys like retinol. These are a small group which are currently available commercially, and that you can utilize as an intelligent sensor. Why such smart sensors are desirable for us? First important point why they are desirable is that they can give you a real time response. Okay? By real time response, we mean that there will be almost no delay between whatever is happening to a system. If there is a perturbation now, within a fraction of a like 1,000 second, that is what we are talking about, you will get the response recorded in your piezoelectric system or in your smart system. That is why these the cameras that can actually record our system in a focused manner much better than earlier days technique is because of the piezoelectric systems present in them. They exploit the functional properties of the material. They have better embeddability. I told you that you can actually, if you consider a particular structure like this, in which you have different layers of composites, you can put your smart materials deep inside. It will not create any disintegration. So, they have better embeddability. Minimal effect on structural properties, very lightweight, high modulus of elasticity, reduction in weight, less power consumption, and better reliability. These are all plus functions for the smart sensors. Now, smart materials, similar to what we have seen during the sensors part, here also I have created a input and an output, and here I have chosen the output as current, charge, magnetization, strain, temperature and light. Okay. And in the input I have given the energies like electric field, magnetic field, mechanical energy, stress, heat and light. Now, if I look at the diagonals like electric field creating a change of current, this is a diagonal element, this is a diagonal element, this is diagonal, diagonal, diagonal. This is not a smart property. Why? Because we know every material, let us take this diagonal, that elastic modulus, every material, no matter smart or non-smart, if I apply a mechanical field, it is going to deform. So, that is not the smartness or the functional property it has, but the smart materials have the property that if I apply a mechanical field, this off diagonal element would say that the output would become a change in current or charge. So, this is a property of some material that you can exploit. Similarly, for some material, the change of stress can create a Villari effect, which will create a change in magnetization. For yet another material, the change in stress can create a change in temperature, and for some other it can create a change in light. These are all can be used as sensors. I will later on tell you that using the other inputs like electric field to create strain, this column is the actuator column, but I will talk about it in yet another discussion. Today, we are only focusing on this part, on the sensors, except this diagonal, because this is not smart. Now, smart materials, they exhibit generally two types of properties. One is called a direct effect, that means the mechanical stress is creating an electric potential, and another is called a reverse effect, that is electric or magnetic field or thermal stimulus creating strain. Remember, the thermal stimulus creating strain is not the same as a thermal strain, it is a phase change. Many times, in fact, the temperature change will create a contraction in the material, not expansion. Now, if you compare them like in terms of actuators or sensors, you would see that their displacement range, if you compare them with respect to the smart materials with the traditionals, you would see that their displacement range is much smaller, but their accuracy is also much higher in comparison to the traditional systems, and the torque accordingly is also smaller, but you can distribute it. The response time that I told you is very fast. Remember, I am comparing here as actuator, but as I told you, most of the smart materials are both sensing as well as actuating. So, whatever comments we make here is also true for the sensors as well. Now, let us look into the direct effect, that means application of the stress creating the change, and what are the materials that can show? Piezoelectric material and polyvinylidene fluoride. So, these are basically piezoelectric ceramics, I should say, and this is a polymer. And magnetostrictive materials, optical fiber, I have already talked about them. Now, the converse effect or the reverse effect, that is the electric field creating these kind of mechanical changes, this you would see in ferroelectric perovskites, piezoceramics, PVDFs. So, many of them you have seen in the other set also. Terphenol D, amorphous made glass for the magnetic field, shape memory alloy you will see corresponding to thermal field, and another one electromagnetorheological fluids, where change in electric or magnetic field can create a change in viscosity. The general properties of smart materials are these three are very important for us. One is what is the free strain, that means if there is no mechanical force, how much of strain they can have. Like piezoelectric material can have a free strain of 1000. Strain is unitless, because strain is actually change in length over the original length. So, it is a dimensionless quantity. Okay. So, here it is 1000 parts per million, which means 1000 into 10 to the power minus 6. Okay. Sometimes we also call it as micron strain, because this 10 to the power minus 6 signifies micron. So, 1000 is for PZT, PVDF 700, terphenol D is more 2000, nitinol is the maximum 20,000, which means it can show a very large change in strain. Modulus of elasticity wise, piezoelectric materials are ceramics, it has a 62 gigapascal modulus, very stiff. PVDF is very soft, terphenol D is lower than piezoelectric material, and this nitinol, which is used as a shape memory alloy, it has basically 2 modulus of elasticity. It is very flexible in low temperature 27 gigapascal and very stiff in high temperature about 89 gigapascal. Another important thing is their bandwidth. Piezoelectric material has the largest bandwidth. High bandwidth signifies very fast response time. So, PVDF is also equally high bandwidth, very low response time. These fellows are little bit slower and SMAs are the slowest. Now, only in one material I will tell you, because the details of all these things I cover in a different course on smart materials, but for the sensing purpose I will just briefly touch on these issues, that the piezoelectricity, the source in the ceramics is like they are actually a ternary structure A, B, O3. You can see that there is one metal, second metal, and then there is oxide. So, you can see in fact here also that these are the oxygens here, which are at the face centers, and then at the vertices you have one metal and titanium is straight at the center. Now, this is generally in equilibrium condition, but if I try to actually expand or contract, then what happens, this titanium slightly shifts its position, and this shift in position immediately creates a kind of a dipole system. That means, a change in polarity happens in the system. That change in polarity that is happening in one crystal is getting in multiple crystals, and if you can somehow basically make all these dipole moments align, then you get a large change, and then there is a voltage that gets generated, which you can sense in the system. And this you will see not only in barium titanate, but in lead zirconate titanate, lithium niobium, lead niobium, yttrium manganese, and these ammonium cadmium family. So, there are a large family which shows this. The perovskite PZT, as you can see, it is one of the best lead zirconate and lead titanate 52:48 ratio, and generally their shapes are rhombohedral, cubic and tetrahedral, and the Curie temperature is important, because beyond Curie temperature you will not see this property in the system. However, fundamentally they all work the same way, the titanium is going here and or the zirconium, and as it is shifted, like it is shifting here, there is immediately a polarity that is happening in the system, provided the temperature is less than Tc, the Curie point temperature. And you can see here the nature of the polarization. So, depending on which way it is expanding, which direction the titanium is shifting, up or down, the polarization nature is also going to get changed. And you can say accordingly the voltage will change. Okay. So, the voltage polarization relationship also you can get it from here with some amount of an hysteresis present in the system. Now, as I was telling that if you do not have any way of alignment, then the voltage indeed will get generated because of the polarization, but they will be random in nature, which means there will be no net effect in them. But if I polarize them with respect to a DC electric field, then they will become aligned, all these dipoles. And then even if I withdraw the DC field, there will be a remnant polarization, and because of that it will more or less remain aligned. In this case, if I further expand or contract, I will get overall voltage in the system, so that it will become a cumulative effect, it will not cancel each other. The way we express it, a very simple equation, two equations we utilize here. The direct effect, the Sensor equation is this one. This is the Sensor equation, and which says that the T is here the stress. So, this is the mechanical stress. Okay. So, we know that the electric field can create the electric field displacement or generate charge, nothing new for a dielectric material, but that the stress can also generate charge because of this electromechanical coupling, that is something that we exploit, and that is the smart material property. Similarly, from the other strain point of view, we know that the stress generates strain, nothing new in it, but that the electric field is generating strain because of this electromechanical coupling coefficient is something which is important for the smart materials. Important to also know that for every such smart material, there is actually not just one to one, but there are a complex correlationship between the electric field, between stress and between temperature. So, in one side we have electrothermal effect in this type of a pyramidal system. In another side we have piezoelectric effect between electric field and stress, and then stress is related to strain, strain to dielectric displacement, that to entropy and temperature. So, it is a really complicated relationship, that is the big picture. In fact, you can actually express the whole thing in terms of tensorial notation, that you are going to have 3 electric field displacements along 3 directions. The charge can generate 1, 2 and 3 depending on the type of stress directions T5, T4 and T1, T2, T3, and you can generate 6 type of strains in principle, though in nature you do not get. For S6 there is no coupling there. So, it is not smart, but S1, S2, S3, S4 and S5, out of them these 3 are actually, you can say, axial strain. So, this is axial and these 2 are actually shear, and the third one is also shear, but that shear system we still do not have any material that actually shows piezoelectricity. The way we see piezoelectricity is present or not is by looking at whether this coupling coefficient is present or not, or so to say whether there is an electric field associated or not. Now, many times the relationship is not so linear, it can be non-linear. So, whatever I have shown you may actually become variation of D, variation of stress, variation of electric field, and the same thing is true for the converse relationship also. However, one thing remains important, that is the coupling coefficient, which can be shown to be the ratio of the piezoelectric energy density square divided by the mechanical and the electrical energy density. So, the higher the coupling coefficient, that means the more energy is getting transformed from one form to the other, like higher coupling coefficient of say 0.9 would mean that most of the mechanical energy is transferred to electrical energy in a system. So, that is the way the K square plays an important role. You can see it here that we have given different properties, density, K31, K33. Now, this 31 and 33 actually signifies that the 3 is the direction of application and 1 is the direction of sensing. So, you can see barium titanate has a low coefficient of coupling whereas this lead zirconate titanate has a better coupling. You can also see that K33 mode is actually much better, because K33 corresponding is 72% of energy that can get transformed, and the D31 is simply talking about electromechanical coupling coefficient in terms of picocoulomb per Newton, and the last column is talking about the compliance modulus of the system. So, this S is not the strain, that is the compliant modulus. So, you can get a comparison of different piezoelectric materials through this table. A few observations you can note here is that PZT family has the highest piezoelectric coupling, and the Curie point of them is 220 to 315, whereas lithium family has a higher Curie point. That is why they are used in applications where piezoelectricity is required at a high temperature. So, they can work as a better sensor than the PZT family because of the high temperature range. And instead of polycrystalline piezoceramics, if you go for a single crystal like PMN, you can get a K33 which is even higher, 0.92, or D33 which is 2070 picocoulomb per Newton. So, that is even better, but single crystals are generally very brittle. That is why we do not use them much. Otherwise, the polycrystals are better. Even better for a dynamic strain is the piezoelectric polymers like PVDF, which has a form 1, that is all trans system that shows this piezoelectricity, and even though their D31 is smaller in comparison to PZT, but they are much more flexible in nature. So, they have a better application. See the various forms, alpha phase, beta phase and gamma phase of piezoelectric. Now, out of them only some forms are good in terms of the piezoelectric property, particularly those forms which shows a higher polarization of the system. That means, most of the things are in one side are actually better, like all the reds in one. So, you can see that is about the PVDFs. Piezoelectric composites also you can make, like a polymer and a piezoelectric powder altogether can give a similar kind of a compliance, and you can use smaller piezoelectric particles and which can be put into polyurethane matrix, and generally up to 120 micrometer particles can be put in silicon rubber matrix, and using this also you can create a polymeric piezoelectric sensing system. Now, here we are showing some of them in terms of actuators and sensors, okay, and this is bimorph configuration, means you have one piezoelectric layer and another one here, or maybe a non piezoelectric layer, and you are applying voltage in both of them in a different way, plus minus and minus plus, so that in one case it is expansion and in the other case it is contraction. So that you can create a bending out of the system. Similarly, a bimorph, if you bend, will respond in terms of the type, the extent of bending can be measured in terms of the change in the voltage. Some applications we only are confined to axial directions. In that case, what we do is that we put a lot of these piezoelectric materials together. So, that is going to create a stack, and then the stack can be used as actuator as well as a sensor. It can be shown that the stacks actually work much better in comparison to the D31 type of sensors and actuators. Why it is so? Because if you look at, I will just go back a few slides where I was showing you the material properties. Actually, if you check at between 3.1 and 3.3, you would see that 333s are much higher. So, that means there is much more energy conversion or transformation efficiency is much better in the 3.3 mode, and that is why you can see that it is actually the stacks are much better. Now, one important thing I want to tell you here is that there is always a particular operating point at which we need to actually use these sensors or actuators. Why? Because I told you, imagine you have a piezoelectric material. Okay. Now, imagine that I am applying a voltage here, okay, across it, and this voltage is going to create a change in the system, and this is when it is completely free. So, which means it is somewhere here, it shows a large deflection. Now, you imagine that I am not allowing it, I am putting some walls that stops it from expansion, but it wants to expand. So, it is going to create a force. So, this is what is the blocking force. Now, in reality, all piezoelectric material is in between this displacement and the blocking force somewhere here, some amount of force, some amount of strain, and we have to design always where will be this operating point. That is part of the design activity. Thank you very much.